North Pole region here. So next slide. Next. Ian.
Sorry, it's, I got some problem with the.
Okay. Yes, but I will continue with the ice skate. Will look like so far we have just the picture on the right corner here, which is one little part of the full array. The ice skate 3D is phased array radar consisting of many small antennas, and each of these antennas are then producing data. And so there is a lot of data that need to be handled in this within the site, and then also between sites. That we have next slide, we can see where the sites are located. They are they are located in the northern Europe, as you can see in the corner there, with three sites of the same size as the one you showed. One in Norway, one in Finland, and one in Sweden. Then the sites are connected with a very high-speed network. So we have terabit links between these sites, which we have got with the collaboration with the university net. Next slide, please. So iSCAT, when it's ready, it will have very large computer storage resources. So when we run the radar in full power mode, which about 10% of the time, we need at least 100 teraflops and about 20 petabyte of storage. And this will be upscaled in about 5 years, and as funding is enough. The data, yes. So during the low power modes or off periods, there's a lot of compute power available for our users. So we are setting up the iSCAT system as a federated or as a high performance center as well. That also secures the sustainability, because then we have all the resources within our control, so to speak. But we of course we need to integrate this with the federations, and so we need mirrors in the federated cloud storage, both for storage and for the applications. We are setting up root shore Dcache we are looking at for the data transfer between the sites and also out from the site. And we need something also for the Far East for our Far East members. And next slide. Next slide. Okay, sorry. We have been looking at a number of techniques. Then, so we have Dcache, as I said, and root shore. We are building our web based on Dirac, which is the data or the user portal for data handling and processing handling. We are using, or we have been looking at the EG check-in for the authentication and authority, and also the B2Find and B2Share search. B2Find is the search, and B2Share is where there's a way to put results from the processing then. So next slide. The data. So we have different levels of data. So the Dirac file is handling the lowest level of data. The B2Share is the higher level is supposed to go into the B2Share, which is the right products of the radar. That is the physical parameters of the ionosphere and atmosphere. We need Geochemistry for the authentication. That is for to authenticate the users, and also to authorize some data that is embargoed. Then, so we have some embargo rules for the lower levels of data. So because of that is our funding, how the funding is done. Then, so each country will have their data for a certain number of time. The Geochemistry is, of course, then we select the Geochemistry because we have a lot of different IDPs, universal university logins, and also social logins.
Ingmar, please, 1 minute.
Okay. Yes. Sorry, I'm almost ready. So we manage this in Perun. So each member is belonging to a group, and the members are then controlling the group. So that is not really under the ISCAT control. Job submission, we can skip that. So here it's an example of some job submissions. Yes, sorry. We have been working quite a lot on the US side. So we started the Madrigal, which is the distributed database. It's together with US for about 15 years ago. It's a database for level 3 and 4 for the data. So it has searches of the physical parameters, and also you can combine parameters. And with these searches, you can either download the data or plot the data. So that is a rather big infrastructure that we are using. ISCAT is also hosting some of the Chinese radar data here. So yes, next slide. And for the EGA's project, we proposed a use case together with GOSC. And that is on the Sunny radar and ISCAT 3D radar, which consists of a similar hardware. You will hear more about the Sunny radar just after me. But both of them are multi-static phased array radars. So it will have separate repositories, but we will try to federate the metadata between them. So the searches will access both of the repositories. And we are proposing also to test the federation, a processing federation, so we can launch jobs in either clouds depending on where the data is. And if needed, there is also a data movement part of this. If we need to process everything on the same place. Thank you.
Okay, thank you, Ingmar. So next speaker is Xin'an Yue. Xin'an is a research professor in the Institute of Geology and Geographics. So he's cooperated with ISCAT. So Xin'an, please kill your time, no more than 7 minutes. Okay, please.
Yeah, okay, but sorry, this is not my slides.
Yeah. So.
This is not my presentation. Sorry.
Okay. Yeah, please.
Yeah, this is mine. So could you please okay, so here's Xin'an Yue from Chinese Academy of Sciences. So I'm going to talk about the potential collaboration and challenges between CESAR and ISCAT. I think Ingmar already introduced very details about ISCAT. So could you next, please? Next, please. So Ingmar already described the ISCAT and also ISCAT 3D. So basically, ISCAT actually is a has been a brand of Europe in space science. So I'm going to so SESAR is actually brand new to the community. It's a we are going to build a modular active electronically scanned phased array and all solid state transmitter and all digital receiver incoherent scatter radar over the low latitude channel. So it's in this picture actually the lower picture show how this radar looks like. It is still under developing. It's going to be ready by the end of 2020. So next please. Then in the future, between 2020 and 2024, we are going to expand. We are going to develop 3 stages of incoherent scatter radar. So basically, we are going to build 2 other receivers in other 2 locations over the Highland Island. So finally, it's going to have 3 receivers and 1 transmitter incoherent scatter radar over the low latitude channel. It's going to we call it the SESAR tristatic system. This system is very similar to is actually pretty similar to the to ASCII 3D. So next please. Next please. So I think there are some time delay. So I'm going to talk when. Oh, sorry. Previous. Sorry. So what happens? So there are some similarities and also complementaries between SESAR tristatic system and ASCII 3D. So basically, they measure the same target ionosphere, and they use the same technology, phased array radar, and also the same algorithm in digital signal processing, data retrieval, and ASCII is the first multiple stations incoherent scatter radar in the world, and the SESAR tristatic system will be the only multiple stations ISR in the equatorial region once developed. Also, we are complementary to each other. First, our geographic location is different, so because we and also we're funded by different agencies. And also scientific focuses are a little bit different. For example, the ASCII 3D will mainly focus on the high latitude ionosphere, such as the precipitation, the aurora, and the SESAR tristatic system will actually cares low latitude ionosphere. So it has a totally different ionosphere phase. And ASCII 3D measure the orange of ionosphere weather because the energy transfers from the high latitude to the low latitude. And the SESAR tristatic system actually we measure the result of space weather. So next, please. And so regarding the potential collaboration between ASCII 3D and the SESAR tristatic system, I think first the technology, because we use the same radar technology and digital signal processing, data retrieval, so we can collaborate with each other to focus on those technology, and also we can collaborate on some science, including the ionosphere physics and also ionosphere irregularity study. And we can do some data exchange and data sharing. And also we can do some campaign to measure some specific space weather event. Okay, so next. The main challenge for us is that actually it is a big data issue. For example, for the phased array radar, the original data is going to be gigabyte in minute. And the final, if you process data to the level 2 to level 3, final data is like a gigabyte in a year. And also, so we face the problem of big data processing, the big data storage. And also, if we want to collaborate between the SESAR and the ASCII 3D, we need the big data transfer and sharing between China and Europe. And also, we need some technical support for online data, online radar control, online data processing, and visualization. Okay, next please. And so we got because Jianhui asked me to talk about the technical support, the technical requirement for open science cloud. So first, definitely we need some computation architecture design for CESA tree-stack system, because now we are on the very preliminary phase of this radar system. We need some computational hardware and software, internet support and storage support. And we need some online system for the data exchange, for running the online campaign and online training. And also we need some technical support to remotely control the radar through internet. And also we want to remotely view the radar, remotely view the whole system through internet. So next please. So I have a preliminary scenario. Actually, finally we are going to have 3 stations over low latitude channel. We call it the Sanya, Haiko, and the Dando. So we need in each station we need some computational and storage system. Then we have a data center in our institute. We need to transfer those big data to Beijing, and also we belong to the Meridian project. We also we need to transfer data to the Meridian project data center. Then we need to exchange data between our data center and the ISCAT, and also we need to open the data to the user, to the community. So actually, we already have some funding support to implement this scenario. For example, our project itself, we have some funding support, and also we have in cooperation with Jianhui to get some funding from Chinese Academy of Sciences to do this this cooperation, and also we have another funding opportunity that we have a cooperation between the ESA and the China Administration of Science and Technology. This cooperation is under the framework for the navigation, but we implemented the ionosphere part into this cooperation framework. So we basically have 3 funding sources to implement this scenario. Okay, next please. I think that's all my presentation. Okay.
Okay, thank you, Xing'an. Thank you very much. So the next speaker is Erica Yin from Academy of Silicon Grid Computing Center. So actually, Yin and Erica and I are good friends. We met maybe 10 years ago. So he will deliver the regional collaboration on disaster mitigation. So Erica, please.
Thank you, Jianhui. Hello, everyone. I'm reporting the status and works of the disaster mitigation capacity building by deeper understanding approach in Asia on behalf of the collaboration leading by Disaster Mitigation Competence Center, one of the competence center in EOS Hub. Next slide, please. The regional collaboration on e-science for disaster mitigation in Asia started from the EU-Asia Grid project in 2008. And because Asia is the most disaster-prone region in the world, and together with 10 Asia countries, that's in the slides, the Disaster Mitigation Competence Center has been focusing on capacity development for disaster mitigation based on deeper understanding approach from EGI Engage in 2015. The deeper understanding approach aims to discover the root cause and the physical processes of target events, and accurate simulations of the whole life cycle of target events are developed accordingly and to quantify the risks. And through such regional collaborations, the distributed cloud regional infrastructure is built up and enhanced based on EGI and EOS Hub compatible technologies. So case study, simulation portal, and knowledge base constitute the framework for disaster mitigation capacity development. And their relationships are described as the top left in the slides. And case study drives the advancement of the science, technology, simulation portal, application, and collaborations. And partners are able to reproduce the hazard events numerically through simulation portals and carry out a risk analysis. And all the observation data, the parameters, simulation portals, event facts, publication, etc., will be compiled into the knowledge base. So based on lessons learned from case studies, a partner are able to make use of the numerical simulations for better risk analysis on other events and conducting their local case studies. And so simulation facilities and knowledge base will be growing and strengthened progressively with more case studies. On the other hand, we leverage existing collaboration framework and opportunities such as the APAN, HR Connect project, and the IGC to facilitate the collaborations to engage new partners and the more local user communities, to host training and the masterclass and to disseminate our works. So altogether, we have at least 3 routine events annually to build up and strengthen the collaborations. Next slide, please. Next slide, please.
So just wait, maybe.
I got a bit problem again.
Okay. Oops.
Next one, yes. For now, 18 case studies of 6 types of hazards in almost every previous one. Yeah, in almost every partner country has been conducted, and 13 of them has finished. So the hazard type covered tsunami, typhoon, and storm surge, dust transportation, flood, forest fire, smoke, haze monitoring, and lightning. And for each type of hazard, the leading scientist or scientist group had been assigned or formed to conduct the deeper understanding of events and developed and validate the simulation processes. And now partners such as Philippines, Thailand, and Vietnam, they could conduct their own case studies based on the deeper understanding approach and contribute to the regional collaboration framework. And from the routine meetings, we support and encourage partners to bring their case studies and users to work with us. In addition to sharing their requirements, case study experiences, etc. Next slide, please. In the next 2 slides, that I will introduce some of the examples from the case studies. So in these slides, 3 case studies results are demonstrated here as examples. The first one is 2018 Sulawesi tsunami case study was conducted because of the complexity in source identification and characterization. A very fast tsunami happened after a scale 7.5 earthquake together killed more than 4,000 people in the northern Sulawesi. So it's unusual such deadly tsunami was not generated by a big earthquake happening along and straight stretch. So according to the scenario study, we concluded tentatively that there are 2 tsunami sources in the event. An earthquake tsunami dominate the impact outside the Palu Bay. Inside the bay, landslide is one possible sources. So that's a very interesting case. However, the location of the landslides are still under further investigation. And the second slide a second study in the right is the dispersion of aerosols from biomass burning in Indochina in springtime of 2018. The simulation captures the root and the sampled concentrations of the dust, 1,000 kilometers long distance transportation. This case also had been verified by data collected from the ground-based gauge in Thailand. And the last example is the typhoon runs through Thailand from South China Sea to Andaman Sea in early January 2019. So typically, the wind speed, air pressure, precipitation, temperature of the whole process of a typhoon could be generated based on the simulation from our simulation facility. Next slide, please. Another case study scenario is like the case on Super Typhoon Haiyan, which caused more than 6,000 life losses in Philippines in 2013.
We got 2 minutes.
Okay. Yeah, turns out most of the life losses were resulted by a storm surge induced by the typhoon. So in order to catch up the impact of the storm surge accurately and timely, so we combine the atmospheric model and oceanic model together to simulate the storm surge effects directly from the evolution of typhoon. And the other challenge is that it's very difficult to precisely simulate the lowest pressure and the highest wind speed of a super typhoon. So in this case study, the simulation model was revised based on the IO physics. So in fact, in short, case study of this collaboration aims to quantify risk and reduce at least one of the dominating factors of the vulnerability, exposure, and the hazards based on the up-to-date knowledge of physics behind the disaster. Next slide, please. So for the distributed cloud platform, the goal is to capture the knowledge learned from disaster case study and support knowledge sharing, reuse, repurposing for broader application, which is still ongoing. Next slide, please. The regional collaboration on disaster mitigation keeps moving on with more case study, more partners, more new types of hazards, more application fields, and of course, more IT technologies. And we also got more regional collaboration from different institutes and organizations from, for example, from UNESCO, from Sentinel Asia, from remote sensing community, from Asian, ASEAN communities, etc. Next slide, please. So in the future, we will carry out more case study. And in the next few years, from next year, this work will be supported from by the EGIS projects. So capacity building for dealing with more complex multiple hazard scenarios all together in these collaborations. And we've been extending this collaboration to agricultural area, leading by Japan, Thailand, and Taiwan, and also extending to space-based resource federation, etc. And systematically, efficiency, authentication, authorization infrastructure, advanced data analysis pipeline, the GPU container Jupyter over cloud are also our focus, and some of them has been implemented in the regional collaboration. The next slide, please. So I'd like to thank all the funding agencies and all the partners in this collaboration. Thank you very much.
Thank you, Eric. Thank you very much. So next speaker is Chenzhou Cui. Chenzhou is PI at the National Astronomical Observation Chinese Academy of Sciences. He will present the virtual observatory and science platform in astronomy. So please, Chenzhou, please take care you 10 minutes, okay?
Okay, thank you, Jianhui, and thanks the organizers for the workshop. So my title, the my title of the presentation is Virtual Observatory and Science Platforms in Astronomy. Next, please. As you may know, astronomy is a big data science research field now. Around the globe, we have many telescopes and observation facilities. With the driven of these facilities, astronomy is a very classic and a leading research fields in big data science. Next, please. So about 20 years ago, the community initiated the idea of virtual observatory to satisfy the challenges initiated by big data. As we know, the web is transparent, and the goal of the virtual observatory is to achieve the same feeling for astronomical data, that it is all available to explore in a single transparent system. So VO will allow astronomers to interrogate multiple data centers in a seamless and transparent way, provide new powerful analysis and visualization tools within that system, and gives data centers a standard framework for publishing and delivering services using their data. And like the worldwide telescope, the virtual observatory is not a fixed system, but rather a way of doing things. The next one. In 2002, the astronomical community, working together with the computer science, we initiated the International Virtual Observatory Alliance. It is an organization that debates and agrees the technical standards that are needed to make the wheel possible, and a focal point for wheel aspirations and a framework for discussing and sharing wheel ideas and technology. Currently, the Alliance consists of 21 national and international members. Okay, next one. During the last 2 decades, the wheel community designed and developed dozens of interoperable applications and services. Here are some examples. And now the wheel framework has been a daily tool, a daily framework for astronomers around the globe. Next one. Additional to this standalone tools, and the VO virtual observatory is embedded in in different kinds of astronomy services now. Maybe you know the ESO VO, the European Southern Observatory, and the Worldwide Telescope from Microsoft Research, ESA Sky, and the CDS from France, Firefly from Caltech, and so there are a number of embedded services for VO for the platform. Thank you. Next one, please. In the scientific data community, we well known FAIR principle, and VO is FAIR from the first beginning of the idea. Next one, please. And as we know, the data amount and the complexity in astronomy will increase steadily in the near future. And the science platforms are being developed to allow researchers to efficiently analyze big data science. And this science platform will enable analyze close to the data and support online data mining and machine learning. Most science platforms in astronomy employ a similar architecture and technologies to provide an interactive data analysis environments. For example, cloud computing platform, Jupyter Hub, and the Jupyter Lab for interface for exploratory data mining and analysis. And we also use container techniques for the interactive environments. And the following, I will give you several examples. Next one. Yeah, this is the NOAO Data Lab. The NOAO Data Lab is operated by the National Optical Astronomy Observatory, the National Center for Ground-Based Nighttime Astronomy in the United States. The science platform provided large catalogs, pixel data, virtual storage, visualization, computer processing, and other services for its scientific users. You can see the URL, and if you are interested, please visit the website. Next one. Another is CANFA. CANFA means Canada Advanced Network for Astronomical Research. This science platform provides the users storage, user management, data publication and data access, batch processing, OpenStack-based cloud services, cloud migration, and the Canada Astronomical Data Center data search services. The interface is very simple, but the backend system is powerful for users. Next. Another one is Science Server. Science Server is a big data infrastructure for science.
2 minutes, okay?
Okay.
2 minutes.
Okay. The principal investigator of Science Server is Alex Zali. Alex Zali working together with Jim Gray to initiate the Sky Server and then the fourth paradigm. And this platform provided the hosted data science, computing services, science-oriented environments, and education materials. Next one. This is from the China VO, Chinese Virtual Observatory. Now the official name is National Astronomical Data Center. The NADC was announced by the Chinese government last year as one of the first 20 national scientific data centers. Our science platform provided a whole life cycle system for the users, from the telescope proposal submission to telescope operation, data archiving, data processing, data publish, and the scientific data publication services. So it is a whole life cycle platform for our scientific users. Next. So this is my last slide. The topic, Global Open Science Cloud, is a very good idea. And all my introduced here, these science platforms in astronomy, we can take them as prototypes for a global open science cloud. Currently, our platforms have been run for several years' time, from idea to research mode for astronomers. But for a global open science cloud, I feel we are facing common challenges and requirements, and we share the same feeling and the same roadmaps. And now the technical solutions have been, and at least partly, implemented and tested. And as a global science infrastructure, GOSC needs strong financial and community support. I know, and I'm confident the GOSC is a very good infrastructure and very useful for the whole science community. So we are very happy working together with all of you. Yeah, thank you.
Okay, thank you. Thank you, Chen Zhou. Thank you very much. So the next talk will be delivered by Guido. Nemoni. Guido is a senior scientist at the European Commission's Joint Research Center, and he will introduce the big data analytic need for Earth observation science community. Okay, please, Guido, 10 minutes. Okay, please.
Yes, thank you, Jean-Pierre. Yes, so I'm going very quickly through this this topic. So instead of astronomy, we are interested in looking not in the sky, but towards Earth, Earth observation. Next slide, please. Then, what we really are seeing at the moment is a real shift. We were used to using isolated images for particular, specific studies with limited spatial impact. Also time-wise, of course, it was also commercial data. So, and what we see now is with the advent of new open sensors like the Copernicus Sentinel program, and of course already the existing Landsat program, but also increasingly outside Europe and the US, the Japanese ALOS program. There's also a Chinese Gaofeng data available under OpenSS. And it's a trend. It's a trend that has basically started with Landsat and is now catching on around the world. And already by now, these systems are producing terabytes per day. Already are stored in petabyte scale annual archives. And for the research community, this is of course a huge challenge to be able to work with all this information. And for that, we generally capture this under big data analytics. And it's basically the combination of having access to this data and then applying the best possible processing techniques, especially now also with machine learning, deep learning, but not forgetting that all this data comes from sensors that have a physical explanation. So also actually the physical models that are behind all this information become more complex, richer in spatial, temporal, and say global domains. And also, in fact, on the side where we start to integrate the validation data. You can imagine that the richer the data sets become, the more you can infer, but you still have to link that to valuable validation data. And what is really important till now, a lot of this has been used in a rather small community of space data users. And what we really need to aim at is to make sure that this data gets out, integrated in a much wider variety of sciences, social sciences, economics, biology, etc., so that we don't that we sort of break out of our expert domain. Next slide, please. So what are the core requirements? You see that already from the introduction, there are currently different use patterns, but they are moving towards these global applications. And this morning, I think we already hit it in the first session where SDGs were mentioned, the needs for these global monitoring systems that derive information on the environment that we can use to assess how, of course, how processes are going, how overall important issues like global change are going to be addressed. And for this, we need a consistent baseline and a consistent monitoring system. The key requirement of this is, of course, to make sure that you have access to your historical data so that all the data that has been collected until now is easily and openly available. And that is a huge data curation task that I think we have not really addressed to the right extent. More technical things that, of course, data needs to be made available in application-ready formats so that you can directly use it in your studies and not being, not having to go through the complex processing things. And some of our sensors actually are not yet up to that level. Then, of course, you can think about, especially in this global context, that the data doesn't have to be at one single location, but can be distributed over different open archives, different open science clouds. And for that, of course, you would then need high connectivity and also ways to quickly move while the user is actually processing its data. So things like smart caching and prediction. Implicitly, of course, with all this data, you need to be able to scale your computing with massively parallel cloud resources. You need to start integrating specialized hardware solutions. GPUs have already been mentioned in all the previous presentations. We think that GPUs are still very limited in their use currently in our domain, in this Earth observation domain. There is actually huge potential in that. And we have, for instance, already some experience with where the use of GPUs is actually no longer compute constrained, but very much constrained by the way you need to get the data from the archive into your computing and then back to the user or back to, say, storage. So it becomes actually storage limited rather than compute limited. And that's an interesting thing to consider in the future. And then, of course, we think that open source is essential, because open source is, if you combine open data with open clouds, then implicitly you're talking about open source solutions as well. Next, please. I just give you two quick examples on what this is really about. So this is, for instance, an example that's coming from our institution. And here we are using radar data, Sentinel-1 radar data, to produce consistent crop map for the EU. And this is actually done with systematically collected ground samples as well. So that combination of reference data and satellite data is very, very important. Next slide, please. This is another example which basically shows this global scope. So this is just a fragment in West Africa, but this is a global product that combines settlement detection on Sentinel-2 with surface water detection based on Landsat, and they have been generated by different groups in our center, and they are now global data sets, some of which you can actually generate in a matter of weeks rather than years as it used to be done previously. Next, please. In our field, we have actually a solution, and that's important, I think, because it's like a target, if you want. So there is a Google Earth Engine, which does this collection of open data, does make it available on a cloud infrastructure. That cloud infrastructure is, of course, not open, but it is free for scientists to use. So that's not an overall bad solution, of course, but there are other issues then that relate to that. And I think what is especially interesting of Google Earth Engine is that they have this, it's not just the data, it's not just the computing, but they also combine it with rich libraries of software that you can apply to this huge data stack, and that also through a very intuitive programming interface. In Europe, we have experience with Copernicus DIAS.
Okay.
2 minutes,
Wait.
yes, okay. This is from the Copernicus Space Program. So these are these are commercial cloud services that try to address this data scaling issue. And they are there are also some other ones in individual member states in Europe. And overall, I would say that the familiarity with these solutions is not so wide. And the next slide, please. Two trends that are important in here. In Europe, we have now started the Digital Europe program that is starting next year, where the European Open Science Cloud is very important. So we see this as a key initiative. There is a specific topic in there, which is called Destination Earth, which deals with modeling and monitoring. So that is especially relevant. It has this European data space concept that is was also mentioned this morning, and that is very important to reach these application sciences. And then there is still a lot of fragmentation there that needs to be resolved. And one way to resolve it is also, of course, not just putting up the particular hardware, but also making sure that the funding streams are directed to use of this infrastructure. Last slide, please. In Europe, we have sufficient, I would say, probably top-notch open source geospatial expertise that can be integrated, that increasingly moves into applied machine and deep learning. And this is still limited to specific groups and needs to be promoted much wider under our Earth observation community. And where then the global open science cloud comes in is, of course, that all these initiatives are automatically scalable to other solutions, portable. It's open source, it's open data. Therefore, it should be very easy to help in the stimulation of open science development. And maybe a last point is that we need to act quick. It's not that this is that we can take another 5 years to think about this. We need to really be ready before the next sensors start operating, and that's already by the end of next year. So I would say, you know, maybe one thing is make this also an urgent issue. I think that is it. My last slide should be my address. So if you have any questions on this, my email address. So if you have any questions on this, feel free to contact me. Thank you.
Okay, thank you, Guido. Thank you very much. So the last but not least, the speaker is Kirsten Neilert. She's from Columbia University. So she will deliver a speech on supporting global open science with collaboration in geoinformatics. So please, Kirsten, 10 minutes.
It's a pleasure to be here. I think I've taken a little different approach in this presentation, in that I wanted to talk about the relevance of collaboration and the challenges that come for it, the drivers behind it primarily. So this is a nice, I think, complementary presentation to what Guido just presented, in that this is not about big data, but geosciences has a lot of small data communities that actually still need to get ready for data analytics and get cloud ready in order to participate in this. Can I get the next slide, please? And I wanted to compare this need of global collaboration for these small data communities with even historic events where basically discoveries have been possible only through global collaboration, by integrating observations done by individuals into a large-scale picture that in this case basically led to defining and understanding the dimensions of the solar system by integrating observations done at the same time all over the world. Can I get the next slide? We have in our community over the last years and decades even done a lot of efforts to collaborate internationally. And this really these collaborations are driven by the scientific needs of integrating data, but also to establish more consistent practices, more consistent data formats and data standards to be able to integrate and better explore, analyze, mine the data that we have. And so I wanted to use this talk to introduce you to some of these activities in order to kind of provide an insight into why these communities have worked together, and think about how these collaborations will fit into a global open science cloud. And on the other hand, how the development of a global open science cloud can build on these activities. Next slide, please. And I think I can more or less skip this, is just reminding us of how many activities are currently going on that pertain to data integration, to infrastructure integration, to capacity building and capacity integration. Next slide, please. So the drivers really in our communities that have made us work together is that we realize we need to converge on essential elements of data infrastructure in its development and operation, which then through more common, more broader adoption become more stable, and also make these capabilities more usable in minimizing confusions for users. We really try to understand and appreciate each other's capabilities, requirements, and constraints, so we don't make the same mistakes or rebuild what already exists. We don't want to duplicate efforts. We want to create efficiencies of scale and share infrastructure where possible, because we're all aware of limited resources to support our data access and data archiving needs. Next slide, please. So the three, or actually it's four efforts that I briefly wanted to introduce here have different perspectives. Some are disciplinary collaborations in the geoscience informatics community that focus either on best practices or on infrastructure. And some are global, some are more national, but still relevant examples, I think, to the Global Open Science Cloud. So next slide, please. The first one I wanted to introduce is an effort that we've named One Geochemistry, and some of you may be aware of an international effort called One Geology that brought together over 100 countries' geological surveys to build a shared and integrated geological map of the world. One Geochemistry seeks to build standards for geochemical data through coordination and collaboration of geochemical data providers, really with the target to make data interoperable and integrated or integrate global data resources. On the other hand, also trying to address the need for the fair data principles with respect to the I&R, the interoperability and reusability that requires development and governance of data best practices. Next slide, please. The One Geochemistry vision is that this would be a distributed architecture where geochemical data are made available from different providers by using the same standard web services. A big aspect of this is sustainability, because many of these small community data providers do not have the funding to operate with a clear sustainability plan. But it requires an international geochemistry community in the first place to come together and agree on standards such as vocabularies and ontologies to enable geochemical data be integrated and reusable following the FAIR principles. What we're doing here is partnering with relevant professional societies as well as science unions and starting off workshops that in the longer term will involve more researchers. We're also working with large research infrastructure providers across the world to create a momentum in the adoption of these standards. And these infrastructure providers are really ready to participate in this because they're struggling to establish and use the standards that will make them interoperable on a global scale. Next slide, please. So a really important component in even for One Geochemistry is the publication of data. And so for a number of years, we have worked with a group called COPTIS, the Coalition for Publishing Data in the Earth and Space Sciences, to foster a dialogue between publishers and data facilities with the goal to implement shared best practices for open and fair data. We created 5 years ago a statement of commitment that was signed by publishers and data repositories. And that became the foundation of a project called Enabling Fair Data, led by the American Geophysical Union, that further went into the weeds of creating recommendations and guidelines for implementing the fair data principles at data repositories and publishers to realize really this full research data ecosystem. Next slide, please. Currently, Coptis is focusing, is basically learning from these first years and focusing on those issues that are still not solved and that are creating challenges, such as a lack of clear and detailed guidelines and workflows, how repositories and publishers can work together. We definitely have a challenge in creating structures for governing domain-specific data best practices. And this is where really One Geochemistry is looking for Coptis to help their challenge of governance. And we're trying to contribute to the discussion on domain-specific criteria for recommended data and software repositories. That is a topic within the RDA, within the World Data System, and so on. Next slide, please. Another international effort that has been really important for this geoscience community is the IGSN as a global unique and persistent identifier for physical samples. This community builds heavily on observations made on physical specimens collected in nature. And these need to be integrated into a research data ecosystem that provides fair, open, transparent, and reproducible scientific results. This IGSN system is already implemented with a distributed architecture with local agents that we actually have members in 5 continents and an international organization that governs this system. Next slide, please. But the success of this system actually now requires it to grow and to become more sustainable and professional. So over the last 2 years, we have been undergoing a strategic planning effort that has been funded by the Sloan Foundation generously to create a sustainable business model for this organization, and to design a more scalable and flexible architecture that can scale to new communities that want to use the system as it moves beyond the geosciences into other sciences like bio and archaeology and so on. And we are in the process of moving these services to the cloud and transitioning to a semantic web architecture. Next slide, please. And the last thing, I hope I will have the time to briefly mention this, is something that is very parallel to developments on a global scale for open science clouds. The US has a Council of Data Facilities that is a common voice basically for data facilities in the earth sciences. And a couple of years ago, they started a shared infrastructure initiative because the data facilities were challenged with new data volumes, with the need for better computing powers, and so on, and therefore joined forces to improve capacity and capabilities and coordinate, converge on technology, and ensure better sustainability and resilience of these data facilities. Next slide, please. So we have efforts going on to create an organizational and social structure to work among these data facilities together with cyber infrastructure providers, both commercial and academic, funded by the National Science Foundation. And in parallel, we are planning a project under the lead of Dan Katz from the University of Illinois to create the prototype of a next generation joint data facility with shared infrastructure in the cloud. Next slide, please. So with all of these efforts, I think it is evident that what we need to communicate is that we need mechanisms to internationally link a lot of different ongoing efforts to build global infrastructure. And for that, we need an environment where all these research efforts can create globally interoperable networks of solid Earth science data, information systems, software, and researchers. And to my last slide, which is just a statement, I think that could lead us well into the discussions, is that we need global collaboration, that we indeed must all hang together. Almost assuredly, we shall all hang separately. Thank you.
Thank you very much. And thank you all the speakers. So we have only maybe 10 minutes to have panel discussion. So I will ask you turn off your camera, and so we'll see. And we had this three questions to discuss, but I think because the time is very limited, so I just want to ask a question to all you. So what's the big barriers for you to use the infrastructure, especially the international infrastructure for your community? And if there is a GeoScope platform, so what's the biggest value for your community, for your research community? I think this may be two related questions. So could you please each one share your experience, your views about this question? Okay. So Rodolphe, could you please say something?
Well, I would say, I mean, clearly, what still haunts us are differences in data formats. Data formats are not yet standardized such that it makes it seamless to go from one place to the other or to join, merge data sets. Of course, the other big issue, which is gradually becoming better, but it's still a lot of work, is to make it, the metadata also coherent, so that it is clear what the data sets are about, without needing to go into all the details of how the metadata has been defined for each of the sites. And then, of course, I mean, let's face it, I mean, if you are looking at distributed research communities, which are sort of worldwide, it is the last mile internet connection, which very often creates a big problem. It is not easy to transfer large data sets. It is not easy for the bandwidths, but it's also not easy for the protocols used. Sometimes transferring a large data set takes days, weeks. And in that case, you need the transfer mechanisms which are reliable, which pick up where you left it when there is a breakdown and so on. And that is not yet in place. So there is still quite a lot to happen before one can really talk about a seamless environment where one could share data and then the resources needed to look at the data. Then we come to the next level of barriers, which are software.
Okay, thank you. Ingmar?
Well, we're working quite hard on the provenance of the data, and it's, as Rudolf says, it's very hard to find good standards. So currently we just make a list of everything that we want to store, and then we try to do some mapping to the few standards that there are available. And it's the same with the data. I mean, we have, but one need to map the data to the standards. So a lot of work is on this semantic mapping then.
Oh yeah, so semantic issue, okay? Yeah. So thank you. Xing'an, what's your opinion about this question? Xing'an?
Okay, thank you. So my main concern is that when we because our radar, our original data is very big. As Ingmar already mentioned in his presentation, that the original digital data is about like gigabyte per second. So in the future, we plan to run the radar operationally. That means probably 24/7 for some sort of purpose. So we needed to do the real-time data processing for this big data. So that's the main challenge for us. And also we want to do the real-time data transfer to our data center from the station to our data center. That's also another challenge for us. The third one also the same question, the same problem as Ingmar already mentioned, is that we have currently we use the data format. That format might be not optimized for this kind of radar. Okay, that's all.
Okay, thank you, Eric. So you show many cases.
Yeah, in my personal opinion, I think the barriers of the research infrastructure, the topmost issue is the quality of the data and the services. All these could be in production quality, and to have the integrity of the data from different sources. The second issue is, in our cases, that's the how to compile all the knowledge from the case study together, and to to be able to share those knowledge and to be repurposed. I think that's the two most issues. And for the probably the long-term development, I think in general, the application-driven strategy is very important for our case, because that could lead the development of the research infrastructure. And we also adopt the knowledge-driven approach so that we can engage the user communities of various domains, such as the scientists, to work together. So from the case study, we can validate the methodology, the quality, the research infrastructure functionality to understand what's missing or if there's any bottleneck, and to build up the collaboration models to ensure the data pipeline, etc. So that's my opinion. Thank you.
Okay, great. Thank you. So Zhenzhou, what's your opinion?
Yeah. In the last few days, I got an email from the International Astronomical Union. They ask for an online survey for research culture. So I feel research culture will be an interesting topic for a global open science cloud infrastructure. For technical aspects, just now several speakers had mentioned, but for a global infrastructure for science community, different research cultures among different communities, different research fields will be maybe a challenge and an interesting topic. Yes, thank you.
Okay, thank you very much. Guido, please.
Yes, just to maybe add two quick points. I think in our community especially, there is this, what I said, this paradigm shift. So people need to move from, location based, or I say on a local station to a cloud. So it's really indeed a cultural effect as well. And with that comes education. So I think one of the real bottlenecks is that too few people, especially in our community, are moving in this direction. So We need education at university level that introduces cloud sources, open cloud sources, also to help stimulate this open science idea. So I think that is really the important part. And then of course all the special hardware, programming, etc. It will come with that, but that's the I think the key point.
Okay, thank you. Okay, Kirsten.
Yeah, I come back to what Rudolf said at the beginning. I think it's the standards, and that's what I try to emphasize in my presentation, that we're still lacking standards which for big data and astronomy and seismic global networks and so on have been established already. But it is also, I mean, clearly the culture of sharing that in these small data communities is still not fully integrated into a world of open science, needs to be advanced. And I think that's actually an opportunity for the Global Open Science Cloud to help these sort of disciplinary efforts to drive community culture. That's a big advantage to have a Global Open Science Cloud there. I do also think that a challenge will exist for data facilities that host the data to participate, because changes to their architecture may be needed that are not necessarily funded. That's one of the experiences that we have had with this shared infrastructure initiative of the Council of Data Facilities.
Okay, thank you. So the time is very late for us, especially in China. It's almost 10 p.m. So I'm very enjoying to this discussion, but I think maybe we should close this session. So thank you all your speakers. You share our landscape of your community, your global cooperation, and the requirement for infrastructure, and even the big challenges. And I really wish all the audience can give your feedback and vote via Slidos. So please see the screen and input your response and your feedback. And tomorrow we will also have 2 sessions. So we welcome everyone can join us. And today I think we should close this session, and thank you all the speakers, all the audience. Thank you very much. See you tomorrow. Bye.
Bye.
Bye.